Okay, today I will introduce a paper called Latent Force Models. It was published at 29. It is an old paper, but it introduced some creative view for the machine learning and dynamic model. The content, the presentation of this report will be consist of two parts. The first is the motivation, and the second is the methodology with example. Because this paper is organized with methodology immediately followed by example, and so I want to introduce in this logic. For many real-world problems like prediction and predictive control, there are mainly two solutions. The first one is the data-driven approach, which combines a dataset with a class of models like neural network, but they tend to suffer from scarce data in a complex system and may struggle in unseen scenarios. The second kind of this approach is deriving mechanistic model based on some physical knowledge. But sometimes they are unfeasible because the model construction is complex and inaccurate enough. Given these facts, the authors point out that the physical knowledge in the mechanics model can be a useful and solid prior to handle unseen scenarios data. For example, the satellite can navigate Mars with unknown data, but the Newton's loops. So in this paper, they suggest a hybrid approach to combine data-driven approach with physical model, and it is emphasized that a hybrid system which involves a mechanistic model of the system can be easily augmented through machine learning techniques. Now let's come to the methodology. The paper illustrates a methodology based on experiment, which is more straightforward to follow like a textbook. But the mathematical derivation is a little bit complex for me, so I'm sorry that I cannot introduce the detailed derivation too much, but I will introduce their basic idea, which is also very useful. First, let's have a look at the latent variable model from the present perspective of machine learning and dynamic system. As you can see, they present similar form. In machine learning, we try to embed data y into latent variable f with parameters w. In a dynamic system, this equation is actually an observation function, which is used to measure the state. You may find it in common filtering. The point is that no matter from which perspective, the useful prior can be added to is beneficial on the latent variable. For example, impose Gaussian process with time dependence, and latent variable is governed by a series of time dependence functions. In this case, we essentially have a latent function model. The authors take a step further by incorporating mechanical model with Gaussian process prior and develop a model with more explicit physical meaning, and it will be also more robust in the absence of data. By doing so, they suggest the latent force model where the term force representing the rule of the dynamic system. The first example is combining a Gaussian process with a dynamic model which can be formulated with first-order differential equation. They introduce a model on biological data. This model explains a phenomenon of a protein factor called p53 driving transcription of some genes. You can see this picture. P53 protein control the transcription of some genes, and they control through some latent force, which is not experimentally observable. Therefore, however, this latent force can be formulated into a differential equation. So the differential equation can describe the dynamic of this process. Therefore, given this equation, whose observation is the Jenny expression indicator, and the latent function has also a physical meaning, is a kind of activity of P53, and By solving this equation, we can have an explicit relation between the observation and the latent function. And I have to say I have not derived the solution, but there is a handbook to address such a problem, which is referenced by the paper. With this relationship, the author modeled the latent force with Gaussian process, and therefore can get the kernel with which encode the relationship between output, input, as well as input and output. Notably, the physical meaningful parameters are incorporated in these new kernels because they introduce the dynamic system into this kernel. And here is the application of this model I summarized from the paper. They first assume a new latent force based on some prior knowledge, and based on this latent force they can formulate a dynamic function based on which they can construct a kernel function for the relationship to encode the relationship between input. And then from this kernel function they can formulate a likelihood for the observation, and then they trade the parameters of this likelihood with part of data, and then after the given the train model, they can sample with trade parameters to check whether the new data is in accordance with the observation. And this picture shows sampling based on the latent force after training to see whether they are consistent with the replica. Next is how second-order differential equation is combined with Gaussian process. The logic is similar, and authors use human motion dynamic model as an example. The observation is the motion angle, but at this time their dynamic model is assumed, so it's not accurate enough. Therefore, the latent force has no specific physical meaning, but there is a mechanic prior which can help regulate the data. And they find the kernel expects a relationship pattern among the latent space and output, and so it is explainable because they have significant patterns. In the application, they demonstrate that their model can achieve better motion prediction than traditional regression model. The last example is utilize partial differential equation with Gaussian process. The dynamic model here is about the diffusion of proton. This process is described by this partial differential equation. Note at this time the latent force the observation is the concentration of each proton over space and time, but the latent force is the concentration of protons at time 0. But at this time, latent force is not explicitly modeled in this dynamic process, but as initial condition when we want to solve this equation. Okay, that's the basic idea of this paper. What they suggest is that their focus has been in building Gaussian process with the characteristics of mechanistic models, so that our data-driven models can exhibit well understood characteristics of these physical systems. And for our own research field, we may want to find how to incorporate the traffic flow theory with the Gaussian process for a better traffic speed prediction. Thank you.